Hello, everybody. So what we're going to be looking at today is section 10.3 and 10.4, which is polar coordinates again. So section 10.3 is polar coordinates, and section 10.4 is graphs of equations in polar coordinates. And yeah, so basically what I'm going to do is just do something that's at the end of section 10.3 and then move on to 10.4. So yeah, so let's go ahead and get started. So we talked a lot last time about how to convert back and forth between polar and Cartesian coordinates, and we had some equations that would help us, right? So like if you were trying to convert from, let's see, I guess it would be Cartesian to polar or rectangular to polar, then we used certain ones. Let's see here, rectangular to polar. Then we used that x is equal to r cosine theta, y is equal to r sine theta, and x squared plus y squared is r squared, but you generally don't need that. Um, and yeah, so that's what you use. And then as an example of that, if you have an equation that's written in terms of not an equation, sorry. Um, if you have a point that's in Cartesian, sorry, why do I keep saying that? Um, Things are hard here. Hold on. Let me back this up. This is a mistake. I said that backwards. I said it correct for equations, but I said it backwards for points, which is what we learned last time. So this is going to be converting a point from polar to rectangular because it solved for x and for y, and you do not need this at all. All right. Now let's go ahead and do this. Move this back up. Okay, so of course that was really easy, right? So if you had convert like r theta, which is as a point, like 3 comma, then we need a theta. So any theta will do here. So I'll say like you know pi over 3, and you wanted to convert it to rectangular. Then what you would do is you would just use the equations, right? So you say x equals r cosine theta, but the r is 3 and the theta is pi over 3, and the y value is 3 sine pi over 3, and you punch those into your calculator and you get a number. So like the cosine pi over 3 is 1/2. So it's 3 times 1/2 gives you 3 halves for the x value. And the sine of pi over 3 is square root 3 over 2. So you end up with 3 square root 3 over 2. And then so in xy, you have xy is 3 halves, 3 root 3 over 2. Okay. And so we did that last time. So we're not going to go over it in this lecture, but that's what we did. And then you had kind of the same thing for converting a point from rectangular to polar, and that was harder. So convert a point from rectangular to polar. And that was harder because you would use, let's see, what did we use? We had that tangent theta is the y value over the x value, um, which then gives you that theta should be tangent inverse of y over x, except that um, you might be 180 degrees off from that because this is only going to give you, like this equation right here is only ever going to give you something between negative pi over 2 and positive pi over 2. And so if you're not in quadrants 1 or 4, you're going to have to add 180 degrees to this, which is pi. You have to add pi to get it in the right quadrant sometimes, right? Um, or theta equals tan inverse y over x plus pi. And that's just if you need it to be in the right quadrant. Theta is in quadrant, I guess, 2, like Roman numeral 2, or quadrant 3, right? Anything outside of negative pi over 2 to positive pi over 2, which is quadrants 1 or 4. So you use that to get the theta, and then in order to get the r is easy at least. R is going to be the square root of x squared plus y squared. Okay, and I don't really want to do an example of that right now, but you can watch the previous lecture for that. So not only can you use that to convert points from one set of coordinates to the other set of coordinates, you can also convert entire equations from one set of coordinates to the other set of coordinates. So if I have something like this, let's see, what do you want to do? Convert an equation from, we'll say, rectangular to polar. Can't spell. Rectangular to polar, or the other way around. Polar to rectangular. Then basically the idea is you used all of the same equations, okay? But you know which one you need depends on the form of the equation that you're using. So you can use any of the conversions above to help you. Okay, so let's just look at some examples here. And this isn't in the homework or anything, but we can just look at it. So like here, going to be an example. I'm just looking for an equation. So yeah, like here would be something simple, right? So like let's look at, going to draw a picture here. We don't have to use a picture, but I'm going to use a picture. So there's a circle. I'm going to make it like radius 3 here. Okay. So there's a circle, and you may know that that has an equation, x squared plus y squared equals, it would be 9 if that was actually, 1, 2, 3, right? So x squared plus y squared equals 9 is a circle with radius 3. Okay, if you want to write that in polar coordinates, it'd be very simple. So in polar coordinates, what you do is you say, well, x squared plus y squared equals 9. And then you just look at that x squared plus y squared and you say, well, what can I find a conversion for that? And you find a conversion, right? And so what are your choices? So your choices for conversion factors are just what we have up here. So you've got this one right here, you've got this one right here. You can use those, right? X is r cosine theta, so you could put that in for x. And also you have one for y, so you could put that in for y. So you could use those, that's fine. But you also have this over here, and you also have this right here. Another way to write this last one is r squared equals, nope, no square root, x squared plus y squared. You can also write it that way. So what you can do is either you use these right here, or you use this one right here. And either one will work, but this one's going to be more direct because we have an x squared plus y squared. That happens to be exactly equal to r squared. So let's just put that in and it'll be faster. So you come here, you say, we notice that x squared plus y squared equals r squared. So if we make that substitution, we'll have r squared equals 9, right? Because this is r squared is x squared plus y squared, basically. Not basically, it is. So then from here, r squared equals 9. That's correct. But if you square root both sides, you could just have r equals 3. and that could be your answer. Um, and that makes perfect sense, right? Because just look at the picture. The radius is supposed to be, or r is supposed to be the distance from 0, 0 out to the curve, or out to the point. And all of these points are a distance of 3 away from the center. So r equals 3 makes perfect sense for this equation anyway. But we did it with algebra right here. Now, not every equation is that easy. Let's pick a different one. Like straight lines are actually difficult in polar coordinates. So like let's convert, let's say y equals, let's just make up the equation of a line here. So let's just say, um, you know, 2x plus 3 to a polar equation. Right, so what would that look like? Well, we've got the equation of a line here. And so the equation of a line, I'm not going to do this to scale here, but we're up at 3, and then the slope is 2. So we have a y-intercept of 3 and a slope of 2. And again, we're not doing this to scale, so I'm just going to draw a line through that point, and we'll just pretend that it has a slope of 2. Right, so there's your y equals 2x plus 3. Now, things that are not kind of not symmetric, but things that are not like in a circle kind of around the origin, like this is not, it's a straight line, is not, related to the angle. Like there's no, it doesn't look obvious what to do for a given like 0-degree angle, 45-degree angle, 90-degree angle. Like how does that give you this curve? So it's not an obvious equation that you would know. And that makes it slightly harder to convert. But we can still convert it because all we have to do is look up at our conversion factors and we'll figure out how to do it. So let's try. So we're going to start with this, y equals 2x plus 3. Now we want to look for conversion factors. So look for conversions for x and y. Now we can't use the simple one that we used up here, right? Like we got lucky that we could use x squared plus y squared equals r squared because we had x squared plus y squared. Well, here the y is over here, the x is over here. It's got a 2 in front. There's no squares. So this is not going to be the conversion that we use. You're going to have to use these over here. And that's not a problem. You just use these. X is r cosine theta, y is r sine theta. So just substitute those in for x and y. So you come down here and you just substitute those in. So the y is going to be, what was it, r sine theta, right? And then we have equals 2x. X was r cosine theta, and then plus 3. So this is your equation here. And then the question is, can you, is there going to be a way that you could, solve this for one of the variables? And, you could solve it for r, maybe. It would be tricky to do, but, if you wanted to try to solve this for r, you could, maybe, this is up to you, solve for r. But technically, we already did it. We did the problem. We wrote it as polar coordinates. It's just, can we write it nicer? If you wanted to try to solve this for r, the problem that you have is there's an r here and an r here. So you would have to move this whole term over to the other side by subtracting it. You would have r sine theta minus 2r cosine theta equals 3, right? So we just moved this over to the other side through subtraction. Now that these are both on the same side, they have an r here and an r here, you could factor out an r. So we'll say factor r out, and you get sine theta minus 2 cosine theta. What that does for you, you see, is that you have the r here, there's only one r now that we factored it out instead of having two like we do on the previous line. So then you could take this and divide it over to the other side. So divide, and you'll get r by itself. You'll have 3 divided by sine theta minus 2 cosine theta. Strange equation, but that's what we get. And that would be your answer there if you were trying to solve it for r. There's other things you could do to try to make that look prettier, but I mean, there's not really going to be a lot of them. So yeah, that's kind of how it goes. Let's do one the other way. Let's try to do this. So opposite, we're going to try example, convert, what do we got? R equals 2 secant theta to rectangular. So this is opposite because we're starting with it in polar this time, and we want to end up in rectangular. So we're starting with polar, right? So how would you do this? You have to think about how to do this. So in order to do this, what you would have to do is say, okay, well, it's actually kind of I won't say it's tricky, but it is tricky. You can't just do it blindly like we did here. Like when you're doing it this direction to polar, you've always got a y and an x if you're starting in rectangular coordinates, and you can always use that y is our sine theta and x is our cosine theta, right? And then that's easy. The problem with going the other direction is if you look at your conversion factors, right, you do have an easy one for r, but you don't have an easy one for theta, right? Theta is this nonsense. So you don't really have a good one for theta. So you don't want to use these very much. You would prefer to use these still because they're easier. Now, the problem with this is that in order to use these equations, you need to have it nicely written. You need to see an r cosine theta if you want to replace it with an x. You need to see r sine theta if you want to replace it with a y. So in order to use these conversion factors instead of these, you kind of have to get lucky. And it's not always obvious that you will get lucky. But in this case, you do. So it's kind of tricky, and you kind of just have to remember it. So, you know, you have to sort of, you have to get lucky and kind of remember some specific examples. Remember a few, examples. To do this type, basically. So what would you do? So on this one right here, we've got r equals 2 secant theta. Well, I know that there are no secants in my conversions. So there's no secants in my conversions. So write it as secant theta, we know is actually 1 over cosine theta. So write it that way. So we go r equals 2 times 1 over cosine theta, like that. And then once you see that you've got this 1 over cosine theta, I can say, well, if I can get the r and the cosine theta together, they'll make an x according to my conversion factors. So we'll try to multiply this actually. We will try to multiply by cosine. And we'll see what that does for us. So if I multiply by cosine theta on the left and I multiply by cosine theta on the right, then what is going to happen is on the right, I'm going to get r cosine theta. I just wrote the cosine theta on the right side. And then here on the left-hand side, what's going to happen, right? We're going to have that cosine and that cosine cancel each other out. So I'm just going to have 2 there, like that. R equals cosine theta. And once you have R cosine, I think I said R equals cosine theta, whatever. We have what we have. R cosine theta equals 2. So if you look back up at your conversion factors, now you just say, well, wait. We have R cosine theta right here is equal to X. So now that we have an R cosine theta, we can replace it with an X. So that's what we do. So we say that this is just X. So it turns out that that's actually a very simple equation. It's just X equals 2. Okay. And that's kind of what you have to do on these. That you're not going to get that lucky where they're simple. Okay. So that's kind of how you go about it. That's all I want to say about that section 10.3. So we're going to get in and do section 10.4 now. So now let's do that. So graphs of polar, well, I'll say graphs in polar coordinates. I think most people would say um, polar graphs or something like that, but it doesn't matter. We'll say graphs in polar coordinate. Let's try to do this. Scrolling down here. There we go. Okay. So there's some stuff about symmetry that I don't want to go into yet. I just want to get it kind of right into plotting. Um, so one of the keys is going to be this. So let me write this down. So let's see. Kind of the way to do these, to make these graphs, to plot curves in polar coordinates. Okay, what can I say about it? So the first thing that you want to realize um, is that it's from what you know about sine and cosine, you should be able to figure out where they are, where a curve is equal to 0. So, yeah, so let's just say that. So, you can often find the angles theta where the radius is 0, or where the radius is maximum. Okay. Another tip is that you should actually just kind of become familiar with some of these graphs if you were going to try to plot a bunch of these. And, once you're familiar with the graphs, then you're not really going through all of the work every time. So it's best to learn specific graphs rather than repeat all the work every time. Kind of to plot them from scratch every single time you see them. And is there anything else I have to say? Um, yeah, there was one other thing I wanted to say, but not really thinking of it right now. So, oh yeah, the basic method is going to be just plotting points like you've done many times in the past. Plotting points that you put in a table. Okay, so let's go ahead and take a look. So here's an example. that we're going to use to test this. So we're going to try example. Plot. What are we going to plot? We are going to plot r equals 4 cosine theta. Okay, so how would we do that? So my strategy, like first of all, you can just make a big table. So you could make a table now, but I'll do a little bit of thinking first. All right. So what thinking would we want to do? Well, the thinking that we would want to do is like what I said up here. Number one, you can figure out the angles where the radius is 0 or where the radius is maximum. So we know that if we're looking at r equals 4 cosine theta, right? You've got a cosine theta there. We should be able to know where this is 0 and where this is 1, or even -1, right? So before we do any work, we can say cosine is the x value on the unit circle. So we know that cosine of pi over 2, cosine of pi over 2 is going to be 0, I think, right? 90 degrees. And, cosine of, you can call it negative pi over 2, but I'll say 3 pi over 2 is also 0. Whereas you've got cosine of 0 is 1, and cosine of pi is -1. And so those are values that you know from, earlier in the semester. And if you know those, then that actually helps you graph this curve. Once you have that kind of information, we're going to actually make the table now. And you'll see why we could have technically skipped this and we would have been okay. So let's make a table. Table. So for your table of values, you're not making a table with x and y coordinates, you're making a table with r and theta. So you go, we're going to put theta and we're going to have r. So what thetas are we going to need? Well, let's start at like 0, right? So let's go like 0, and we could do 45-degree increments to kind of how much trouble you want to go to. Um, I guess I'm going to go 45-degree. You could be doing this like you could be going like pi over 6, 2 pi over 6, 3 pi over 6, which is pi over 2, 4 pi over 6, 5 pi over 6, pi. You could do it that way. That's a lot of work. Because you see, we've only gotten from 0 to pi, so then you'd have to make another table. I guess we'll just do this because we already started it now. 7 pi over 6, 8 pi over 6, 9 pi over 6, which is 3 pi over 2, 10 pi over 6, 11 pi over 6, 12 pi over 6, which is 2 pi. So that's all the way around the circle. So that's a lot of table values. And then you could calculate the R for all of those. And you would just grab a calculator for that, or use what you know about the grid functions here. So what would you do? So you're just going to be putting these theta values into the equation. So like the first one's going to be 4 cosine 0. So what's that going to be? Well, cosine 0 is 1. So we know that this is going to be a total of 4. And then you put in your pi over 3. You're going to get like 3 square root 3 over 2. Oh, that should have been 4 square root 3 over 2. Right? So I'm going to get an approximate answer on the calculator here for cosine 5 over 6. What? Oh, I'm not in the correct mode here. Hold on. Calculator hard. Okay, where is setup? No. Well, where's the stupid mode button? Man, option, menu. I'll find it. Life is hard though. Oh well, I give up. I'll use my other calculator. Um, takes more button presses, but radian mode 4, cosine, pi over 6. Right. Yeah, I know it's 2 square root of 3. That's about 3.46. Um, pi over 3, so you're going to have 4 times cosine pi over 3. That's going to be 2, of course. This is going to be 3 pi over 6 is 0, right? So 3 pi over 6 is actually pi over 2, so that's going to be 0. Um, and then we're going to go negative, and this is going to be negative 2, negative 3.46, negative 4, negative 3.46, negative 2, 0 again. And this is going to be, where are we? I guess 2, 3.46, and 4. All right. So you can use a calculator to get all those values. Now, what are you going to do with those values? Well, you're going to start putting those on the graph here. So we're going to need graph paper. So let me get a table here. Oh, I have to use that one. I thought I just saved a better one. That's unfortunate. I had a better one than this that I wanted to use, and I don't know where it is now. Okay. So there's my graph paper, and we need to start putting in numbers. Actually, you know what? Let me come back here. This is the one that I tried to save. To photos, copy it. Try that. Delete. No, see, we don't got it. Okay, well, here we go. We'll use this one. Okay, so come on, go. Stop doing that. It won't let me put it off the page here. Okay, good enough. Okay, so we want to plot this. So you have to go find the angle and plot the point. So, right, we've got 0 for the angle. So this is the 0 for the angle. R equals 4. So we got, what do we have? Like 1, 2, 3, 4. So that is right here. And then your next angle is pi over 6 and about 3.5. We're not going to get that perfect, but we'll try. So pi over 6, right? So we're looking right here, and we're at 1, 2, 3, and about 4. We're about right there, like that. And then we've got pi over 3. That's pi over 3 when you reduce the fraction, comma 2. That's pi over 3, comma 2. That's going to be here. Then you've got pi over 2, which is straight up, but the radius is 0, so we're right here. And then this is going to be a little bit confusing here. Let me actually, I don't want to have to redo this here. So closing Notability because it's really laggy. Open it up again. Here's my notes. It lost my title. Okay, we're missing a couple points, but that's fine. So what did we have? We had pi over 3, comma 2. pi over 3 comma 2 is right here. And then 0, 0. Okay, good. So this is where we were. And then we keep going. But when you get here, you're at 4 pi over 6. 4 pi over 6 is 2 pi over 3. So this is, 4 pi over 6 is right here. And so in this direction here is the direction you're supposed to be going, but the radius, right? The radius here is -2. So we're not actually going up that direction. We're heading in the opposite direction by 2. So it's actually -2 in that direction would be instead of 2, 2 would be right here, but that's wrong. You would want the opposite direction, which is this way. That's the one you want, right? So from here, +2 is here, -2 is here for the radius, right? If you're heading in this direction, +2 is this way, -2 is the opposite. Okay, so gotta erase this. And they're all going to be that way. So like on the next one, where you've got 5 pi over 6, 5 pi over 6, of course, is right here. But opposite 5 pi over 6 is 11 pi over 6. So instead of having a point at 3.5, right, that'd be like 1, 2, 3, right? Instead of having a point there in that orange circle, it's going to be the opposite direction of that orange circle. So it's actually going to be 1, 2, 3, about here. Like that. And then the same thing for the last one here, where we've got pi comma -4. Of course, pi is here. So the opposite direction is going to be over here. And so instead of having 1, 2, 3, 4 here, it's actually going to be here, where there happens to already be a dot there. So there you go. Now, the curve that we make then is just going to be tracing through these points. So you start at this 0, 4, and then we went up here, and then we went over here, and then we went down to 0, then we went over here, and then we went over here, and then we went over here. And so that's our curve for that first table. Now, if you keep going on the table, you're going to see something interesting happen, which is going to be like you've got 7 pi over 6, which is here. It's got a negative radius though. So instead of being -3 point something, which would be here, or instead of being 3 point something, which would be here, it's going to be the opposite direction, 3.46, which is here. There's already a dot there. Okay, so when you plot this line right here, or this dot right here, it's going to be here. This one right here ends up right here. And if you keep going, the same kind of pattern is going to happen where, get the pointer back. So like this point right here, 8 pi over 6, which is 4 pi over 3 here, we're supposed to be at -2. So +2 would be here, -2 would be here. There's already a dot there. So these points right here just happen to be a repeat of these points up here that we already plotted. So if you actually go through and you trace from 4, like if you trace these points and then you trace these points, what you get is, so starting at this point, you're here. First point, second, third, fourth, fifth, sixth, seventh point. And then the second table is 8th, 9th, 10th, 11th, 12th, 13th point. So this table right here is just tracing around the entire curve again. So this is around the table around the circle once, and then this part of the table is around the same circle again. And if you made a table going past 12 pi over 6, it would go around a third time and a fourth time and a fifth time forever, right? Because these functions are periodic, so once they've traced through all their values, they just kind of trace through the same values again, over and over. Okay, so there, we plotted this curve. All right, now what I want to do is I want to grab these pictures for you. So let's go to your book. trigonometry. I don't know why I don't have it up right now. We use OpenStack. Get it here. Table of contents. 10.4. I just want to steal a particular image. That's what we're doing here. Yeah, so here's one that they plotted for you for themselves. This is not the same one that we plotted. That's why it above zero, like that's why it's vertical instead of horizontal. That doesn't make sense. It's a circle, but that's why it's where it is. It's not in the same place as the one that we drew. Uh, and here's the different possibilities that you could have. This is what I wanted. Copy. It's Discord, right? So here's some circles. And so, of course, we plotted one for cosine theta. And so that's this right here, right? A cosine theta with a positive gives you this circle. So yeah, so we did. So circles. I mean, you can see that they're circles, but they're circles. Okay. And now, what I was saying up here, where I said it's best to learn specific graphs rather than to repeat work to plot them from scratch, that's absolutely true. You'll see why momentarily. So if you look, there's another type of graph they call a cardioid. Limaçon, I guess, looks French. These are ones that have loops. What do we have? We got some figure eights. We got rose curves. We got all kinds of stuff that we could plot. Got spirals, and you can kind of summarize some of the graphs here. And I'm gonna copy these and just paste them into my notes. These are going to be, what are they going to be? Some polar graphs. And then we'll plot a couple of these after I copy paste these. Okay. So these are just some of the polar graphs that you might have to plot, not have to plot, but that you could plot. And so we're just gonna take a couple of these and figure them out. So I think what I want to do now is let's plot one of these guys here, like odd petals here, odd petaled rows. So they say that it should be r equals a cosine in theta, and that or r equals a sine in theta, and that's going to be if n is odd, or if it there will be in petals. Okay. Now the reason it says in odd in petals is because if you look at these, this one over here, whatever the n is, there's actually twice as many petals. So like if n is 3, there would be 6 petals, like petal, 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 petal. Whereas if you pick n to be an odd number, then you don't get double that. So like if n is 5, you get 1, 2, 3, 4, 5 petals. This one, 1, 2, 3, 4, 5, 6, 7, 8. This is actually n equals 4. So n equals 4 has 8 petals, and n equals 5 has 5. You get twice as many if you have an even number. Why is that the case? Well, we could plot them and figure that out, why that would be the case. But you'll see that it just happens. So let's try this. Let's try these. Is it still smooth? Kind of. All right. So let's plot one of these by hand, right? We're not like we've got it written there, but let's do it by hand. So example. Plot R equals, um, let's just do 3. And we could do a sine or a cosine. Let's do a sine. 3 sine theta. Okay. Oh, no, that's wrong. Wrong place for the 3. 3 theta. Okay. And the A is going to be just how wide the graph is. Like if I want to put like a 5 here, for example, that will just make it go out a distance of 5 from the origin, right? So that's just how big it is. Now, if we're going to plot this from scratch, like this is where you get back into what I said up here, where I said it's best to find the angles theta where the radius is 0 or where the radius is maximum. And so the way that would apply here is you would look at this curve here and you would say, well, we know where is the sine, because we got a sine, where is the sine 0 and where is the sine maximum, which would be 1 or -1. So we know that sine theta equals 0 when theta is what? Well, sine 0 is 0. So when theta is 0, or also pi, right? It's actually not just those, right? If you keep going, it's actually 0, pi, 2 pi, 3 pi, 4 pi, etc. Like all those are going to be where theta is, uh, what's it called? 0. All those where the sine is going to be 0. Sorry, doing it again here. Okay, good. Uh, nice and smooth again. Okay, but we do not have a sine theta. We have a sine 3 theta. So this is not what we have. We have 3 theta. So what's that mean? So instead of when theta is all these numbers, we would have 3 theta instead of theta. So for us, 3 theta equals 0 or pi or 2 pi or 3 pi or 4 pi or 5 pi, dot, dot, dot. And so if you took that, 3 theta equals those angles, and then we divided by this 3 here. So if you just go over 3, 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 dot, 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 then this would be telling you all of the angles where the radius is 0. So we know r equals 5 sine 3 theta um, will be 0 when theta is 0 or pi over 3 or 2 pi over 3 or 3 pi over 3, 4 pi over 3, 5 pi over 3, dot, 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 right? All of those angles. And so what's that mean? Well, what that means is if you look at a graph now, so well, that's not the one I want. Delete. Let's do it again here. We'll steal this picture again. Okay. So what that's telling you is all of the places where the radiuses should be 0. So if you mark those out, so like I'll just mark those out in kind of a light color here. So theta is 0. So if I come out here, I go, that's not what I want. It's a little bit too light. Okay, hold on. Big. Okay. So if you kind of just from here, that there's 0, and then the next one is pi over 3. So that's here. And then the next one is um, 2 pi over 3. So that's here. And then the next one is 3 pi over 3, which is over here. And the next one is 4 pi over 3, which is here. I don't know why I'm kind of doing dotted lines, kind of not. The next one's going to be 5 pi over 3. And then the last one is 6 pi over 3. Well, I mean, if we keep going, but I stopped writing them right there. The next one would just be one that we already drew. Now, here's the thing though. If you look at these, so what I drew so far is not the graph. What I've drawn are the angles where the radius is 0. And what that's saying basically is you're going to have those petals that we know we're going to get from this right here, right? So these petals here, you're going to get in between uh, kind of in between these angles here. Okay. And wait, why is it so far down? I don't know. So those are going to kind of mark off the places where the radius is 0, basically. So if you come and you make your table now, when we're making our table, it might look like this. So you've got your theta right there, and we're going to calculate the r right here from, for what was it? Sine 3 theta. Like that. And if you go and you calculate these, um, so like we could use 0 as our first angle, right here. And then don't jump to pi over 3. Don't jump from here to here. We should take kind of halfway, the pi over 6. So let's do pi over 6, then do pi over 3, and then we should take halfway between here and here. So let's do pi over 2, and then 2 pi over 3. So I'm going from here to here to here. Then I want to go to 5 pi over 6 and pi. Keep going. Looks like 7 pi over 6, and then 4 pi over 3, and then 3 pi over 2, and then 5 pi over 3, and then we're back at 2 pi, which should take us all the way around the circle. And let's figure it out. So you go and you calculate these on your calculator here. R equals 4 sine, in this case, 0. 0. So that's 0. And then you've got 4 sine pi over 6, which is a half. So that's going to be 2. And so the same kind of thing that happened to us. Wait, that's wrong. It's 3 theta. I put theta. So the first one was correct though. 3 times 0 is 0, so that's 0. But the next one you have to do 3 times pi over 6, which is pi over 2. And so 4 sine pi over 2 is going to be 4. And then when you do 4 sine 3 times pi over 3, you're going to get 0. Remember, the pi over 3 and the 2 pi over 3 and the pi, like all the ones that I marked off here, are going to be 0. And so actually what happens here is that if you actually go through and you calculate these values, it just alternates between 0, 4, 0. Well, I guess I should take anything for granted here. 4 sine 3 times pi over 2, which is sine of 3 pi over 2 is going to be negative 1, so it's going to be negative 4. The next one's going to be 0, then it's going to go positive 4, and then it's going to go 0, and then it's going to go negative 4. And it's going to go 0, and then positive 4, and then 0, and then negative 4. That's what. Wait, something bad happened. Oh, I missed one. I was going halfway, then halfway there. So skipped an angle. I skipped 11 pi over 6. That one would be -4. And then 12 pi over 6, or 2 pi. 0. Okay, left one off the list. So if you go and you plot these, we're going to plot these exactly the same way that we did for that other curve here. So what happens is 0, 0. Well, that's right here. How come I can't? Oh, 0, 0 is right here. Okay. And then you've got pi over 6, 4. So that's 1, 2, 3, 4 here. And then you go this one, pi over 3, 0. That's this direction, but the radius is 0 again. And what happens is this. So like a 0, 4, 0 section means that the graph goes like this. It goes from 0 at this angle, comes out to 4, and then by the time it gets to pi over 3 here, it has to go back to 0. So in each of these little sections, it goes out, and then it comes back, out, and then it comes back. So like these lines that we drew here are kind of the outlines of the petals. It does that. And that's the first 3 points, right? That's this. That's one petal. So then from here to here, that should be another petal. So that's going to be, but you also have to take into account that this is a negative radius here, and that will change things as well. So when you're tracing through these again, you got pi over 3, 0. So that's here. Then you've got pi over 2, but it's a -4. So pi over 2, 4 would be right here, right? That'd be pi over 2, 4. But we got pi over 2, -4, so it'll be down 4. So 1, 2, 3, 4. So it's actually down, and moved it again rather than drawing on it, down here. So it actually, instead of being a petal up here like that, it's actually a petal down here. That. And then you've got your next petal here. Another, oops, actually, no, not right there. That. 0, 4, 0, and that's 0, 5 pi over 6, 4. So 5 pi over 6 is here, and that's +4, so that's out here like this. So it goes out like, that's not what I was trying to do. So it goes out like this, comes back. Then you got this section. So that's this section here, right? From pi, 7 pi over 6, 4 pi over 3, pi, 7 pi over 6, 4 pi over 3, this section. But you're not going to have, again, you're not going to have a petal there because the radius is negative. So instead of having a point here at 4, it's actually -4, which is over here, and that's the one we already drew. So this one, oops, this one, and this one are all repeats. So this much right here, these are going to be 3 petals that overlap the first 3 petals that we already drew. So there we go. Now just a comment about how this is traced out. So as the angle, right, the angle goes 0, like goes around like this around the circle, right? 0 up to pi over 2, pi, 3 pi over 2, 0. But the tracing goes like this. As the angle goes up, and you can just follow along here, it goes 0. Then as we go this way, it goes out here, comes back. Then it goes down here, comes back. Then it goes over here, comes back. So it actually traces this in a smooth fashion. It doesn't go petal, petal, petal. it doesn't take like a sharp, like it doesn't go one petal and then take a sharp turn. There looks like there's a corner right here, but there's no corner. It actually traces out this way. It goes petal, but it keeps going in a smooth fashion. Petal like this. Okay. So that's three petals. So we saw that it did exactly what it should, right? N equals 3, which is odd. So it matches up with, so part C there says 3 petal rows is what we should get. Okay, so we plotted a 3 petal rows. And, plotting all of these is very similar. Like this is kind of a 2 petal rows. Um, these are kind of 1 petal roses, if you will. Um, and yeah, so you can plot all these on a computer as well. So I recommend that you try Desmos for this. So if you go desmos.com, grab a calculator. Here we go. Now, might take me a second to get polar plot. I think I don't need to. Oh yeah. So if you look at the grid here, I can click on buttons here. So we can go them. And once we do that, we just type it in here. So we can say like R equals, I guess I have to do keyboard. R equals, how do I get an equals? Equals, and what did we just plot? 5. Was it 5 or 4? I don't know. It was 4. 4 cosine. And we can call it T, maybe. That's not what we wanted. Theta. Okay. So there was I think the first one we plotted, or something like that. What do we want? We want 3 theta though, right? So we need parentheses. Sorry. It's hard to do this on the keyboard here. 3 theta. There we go. And once I do this, do something else here. I can put like delete this, and I can put like a variable here. We'll go capital A, and it'll say you want a slider for A, and I say yes. And then I can change the bounds here. I can say let's go from 1 to, let's say, 10. No, let's just say 8. And the step size should be 1. And then I've got a slider here. So if you want to see 4 cosine theta, this is 4 cosine theta. Let me make this bigger. Where's the projector? Okay. So there is 4 cosine theta. If I go here, this is 4 cosine 2 theta. 4 cosine 3 theta, which has 3 petals. 4 cosine 4 theta, which has 8 if you count them. 4 cosine 5 theta, which has 5. 4 cosine 6 theta has 12. 7 theta has 7. And 8 theta should have 16 petals. Right? So there's all of our petals, our roses, I should say. Now, what else can we do with these? Well, we can do more. First of all, what happens if you change it from a cosine to a sine? So here's what it'll do. So here's 4 cosine 2 theta, right? 4 petals, but notice where they are, right? They're like horizontally, vertically oriented, right? One left, right, up, down. If you change this to a sine, you still have 4, but now they're at a diagonal, right? Instead of being centered along the axes. But other than that, it's the same basic idea, right? The number of petals as we kind of scroll through them is the same, but they're all just rotated by 45 degrees. So that's all the sine or cosine does differently then. What else can we do? Well, we can look at some of the other graphs. Um, so like if I take that off, take this off, they say that this is one of our graphs, A minus B. Let me do B, A. Add a slider for B. Um, so basically, what you've got here is you can go from a circle here, if B is 0, and then as you change the constants A and B, it goes from a circle to what they call a limaçon, or butt, looks like a butt. Keep going, and you get a little loop in there, and it gets bigger. So you can see what happens with A minus B sine theta. If you change that to A minus B cosine theta, that's just going to change the orientation again. Cosine, left and right instead of top and down, top and bottom. Um, so there's that kind of shape. And that really, this kind of thing here, and the roses, I should say, are one of the interesting ones that you had on your list of stuff that you could plot. Okay, now these are harder to plot. Um, Basically, what's happening here, I guess you can't write on it, but basically, what's happening is for the big loop, that would be like angles 0 to like pi or something. Um, but then the little loop would be like um, different set of angles. And so what happens is like there should be a loop, like there should be kind of sorry, oops, that's not right. Um, so you could think of like this kind here where you've got like a two petal rose. But what if the petal on the right was actually inside of the petal on the left? Then that's how you get the inner loop kind of graph. So that's what's going on there, and the exact number relationships that make it do one graph or the other graph. Um, you know, we saw that it's how big the A and the B are in relationship to each other in terms of the R equals A plus B cosine theta. How big are the A and the B in relation to each other? Depends, tells you whether you get that loop in there or not. So whether it's a but or whether it's got a loop. Okay, let me put this back up here that I accidentally moved it. Yeah. So I think that's pretty much it. We're an hour and 8 minutes into this. So that's a basic rundown of how to plot these. And I recommend that you check out Desmos and just plot some of the curves that you see here. Either put in numbers or put in um, if you type in an A and a B, it'll ask you if you want to add a slider, and you can move the sliders around and see what that does to the graph. Um, yeah. Okay, so that's it for now. Um, this is not on your homework, but we're doing it anyway. We got some time. All right, talk to you guys later.